Okay, with our definition of subgame perfection in hand, let's take a look at another example. And this is another prominently studied game. Probably, you might say it's the most studied game in the experimental literature. So there's literally hundreds of papers that have studied this game. So it's known as ultimatum bargaining. It's a very simple bargaining game, and yet one that's sort of intriguing in the way that people play it. So what does it look like? It's a game where one player makes a take it or leave it offer to the other player. So player one makes an offer to player two, so they can split a pie, split some prize. They say, here's how much I want, here's how much you get. And then player two can either accept or reject it. So they can either say yes, and then that split is implemented, or they can say reject, and they say no, and then what happens? Everybody gets zero. So in particular, let's look at a version of this game where player one makes an offer of X, which lies between 0 and 10. So just keep it in terms of integers. So 0, 1, 2, 3, 4, up to 10. They can make an offer. And this offer is the amount that player two will get. So then player two can either accept or reject that offer. If it's accepted, then player two gets X, whatever player one offered them, and player one keeps the rest. Okay? And if it's rejected, then both get 0. Okay? So we can represent that as a extensive form game, a simple game tree here with perfect information. So player one moves first. What are their choices? They are choosing how much to offer player two. They could offer 0, 1, 2, 3, etc., all the way up to 10. They could make any one of those offers. So we have 10 different branches leaving the first node. And then for each one of those, player two can either reject it or accept it. If they reject it, no matter what they're rejecting, it's 0 for everybody. If they accept it, then whatever the split was is implemented. So if player one offers 1 to player two, then player two, if accepting, gets 1, a payoff of 1. Player one gets a payoff of 9. Okay. Okay, so now let's solve this by backward induction, which in this case is going to coincide with the subgame perfect equilibrium. So in this particular case, every positive X is going to be accepted by player two. If offered 0, player two is indifferent, could accept, reject, or mix. But otherwise, player two accepts every positive one. And then player one is going to either offer 0 or 1, depending on what 2 is doing at this 0 node. So in particular, if we go through and sort of solve this, anytime player two is offered a positive amount, if we're looking at a node where they're making a choice between 1 or 0, well, 1's bigger than 0, they like the 1, they should accept. If they're offered 6, 6 is bigger than 0, they should accept. And so we end up with accept everywhere here for any positive, 1, 2, 3, all of those have accepts. The only case where they might reject is when they're offered 0, because then they're getting 0 either way, and so they're indifferent, and so then there's no prediction of exactly what player two should do. Okay, so in this case, so player one's choice here, given that player two is going to accept something as low as 1, player one is either going to offer 1 or 0, depending on whether player two is accepting or rejecting at 0. But the prediction here in terms of subgame perfect equilibrium or backward induction rule out any offers that are 2 or above, and the only offers that will ever be made are either 0 or 1, and then 1 is always accepted, and 0 might be accepted, it might not, depending on the particular specification. Okay, let's just compare that to the set of Nash equilibria in this game. Set of Nash equilibria are fairly large in this game, and in particular, here's a Nash equilibrium. Pick any X, and then have player two reject any offer that's below X, any lower offer than X, and have player one and accept an offer of X, and have player one offer exactly X. So player two rejects any offer below X, accepts X, and player one offers exactly X. Why is that a Nash equilibrium? Well, it's a Nash equilibrium because if they're offered X, they can reject it, they get 0. They accept it, they get X. X is at least as good as 0. So the player 2 accepting X is fine. Player 1 is doing the best they can, given that player 2 is rejecting everything below X. So this is the lowest possible offer they can offer to player 2 that will be accepted. So that's the only way they can possibly get a positive payoff. And is player 2 rejecting any offer below X reasonable? Well, they're never offered anything below X, so it is a best response and part of a Nash equilibrium. It's not necessarily part of a subgame perfect equilibrium. If X is bigger than 1, then rejecting any offer below X is not part of a backward induction solution, but it is part of a Nash equilibrium. So basically, there's lots of Nash equilibria here. You can support pretty much anything. Subgame perfect equilibrium or backward induction solution, iterative logic here, says that player 2s should accept pretty much any positive amount that they're offered, and player 1 should offer either 1 or 0. Right? So we've got this contrast, backward induction. Player 1 gets either 9 or 10. Player 2 gets either 1 or 0. Nash equilibria for any X. Player 1 gets 10 minus X. Player 2 gets X, so there's lots of those. Okay, let's have a look at what actually happens in some of these games and why there's so many experiments about this. So here again is some data from a game theory class at Stanford, where the students could offer exactly the amounts that were there before. So these are the offers, the X's offered by the player 1s. So these are the X's that are offered. The average in this was 3.5, median 3.0. When you look at the frequency here, what do you see? Well, you see a bunch of people offering 5, some people offering as much as 9. You see some scattered other ones, and you see a bunch of 1s. So if we were doing the backward induction solution, you would expect either all 1s or 0s. You see a few 0s as well, but everything should be down here from backward induction. Whereas you can support these as Nash equilibria. But the backward induction does seem to give us some idea that we're seeing more accepted there. But there's also some play up here, which indicates that some players are expecting to have lower things rejected or might have other motives in mind. What about the acceptances? So what happens on the second move? So basically, we can think of what's the lowest amount that players would accept. Actually, there's many players who would accept 1 or above. There are a few players that held out for more. Some 5 seems to be a prominent number. That's a 50-50 split. There were even some players who would only accept things that were even bigger than 50%. So there were a few players that demanded more. But most of the players actually were consistent with the backward induction solution of taking anything they could get. So this was actually a game which is somewhat atypical of what is found in a lot of experiments, where they tend to deviate a little bit more from the backward induction solution. This one, a lot of the players are playing something that looks pretty close to backward induction, and a few straying away from that. Let's have a look at some of those other experiments just to get a feeling for what happens in these games. So this is a paper by Slonim and Roth, 1998, Econometrica. And they ran ultimatum experiments in the Slovak Republic. So one of the questions that actually often arises in experimental treatments of game theory are whether or not the laboratory is a good predictor of behavior, because often when we think of applications, the stakes might be quite large. So if we're actually thinking about bargaining over a house or bargaining over wage contracts, things like that, the sums can be quite large. And yet in the experiment, we're offering small amounts, and it might be that people behave differently with small or large amounts. So what they did is they ran a series of experiments in the Slovak Republic, and they had a game where you could offer any integer between 0 and 100. So for instance, if you offered 459, if player one offers 459, then they keep 541 units. And how much those units translated to in terms of payoffs, what they did is they varied the amount. So they had one set of experiments where the total amount of the pie was worth 60 Slovak crowns, another where it was worth 300 Slovak crowns, and a third where it was worth 1,500 Slovak crowns. Now, the average monthly wage in the Slovak Republic at the time of these experiments was roughly 5,500 Slovak crowns. So actually, this high-stake version is almost a week's wages. So 1 week's wages is a fairly substantial amount. So they're not playing for small amounts anymore. They're playing for, the pie to be divided as a week's wages. That's a fairly substantial amount. And so the question is, how do people play in those games? So let's have a look at some of the outcomes that they got. First of all, let's look at the offers that were made by the first player. So actually, it's fairly interesting here. So we can look at the 60 crown game, so small stakes, medium stakes, and then a week's worth of wages stakes. And in all three cases, the averages are above between 400 and 500, say mid 400s. So almost 50% of the pie was offered to the second player. The medians were actually even closer to 50%. So the medians are hovering just below 50% in terms of how much is being offered. So, one thing one can question, it's fair, almost fairness. So you're giving almost half the pie away. Or, how are they anticipating the responses to look? Let's look at what happens in terms of the responses in these particular experiments. So let's look at, say, fairly low offers. So offers between 0 and 245, which is just one of the cutoffs that were used in the analysis of the data. So how often were these low offers rejected? So if we look at the low stakes games, the 60 Slovak crown games, 100% of the time, if a player was offered 245 or less, they rejected those offers. When the stakes went up to 300 crowns, so the medium-sized games, then we end up with a rejection rate of 91%. So 91% of the time they were rejecting these low offers. And then once we get to the week's wages, then that rejection rate drops to 60%. So it's still a substantial rejection. They're rejecting 60% of the time they're rejecting these low offers, which means that they're rejecting non-trivial amounts of money. But that 60% can also help explain the numbers we saw just before in terms of these high offers, because you have a high chance of being rejected if you go to a low offer. So the first player is indeed anticipating that the second player might reject the lower offers and is reacting to that. Now, exactly why second players reject and why first players are offering this much is a subject of a lot of debate, actually, in the profession. So part of the reason there have been so many different experiments run is to investigate what the motives of the first player are. So you can run these same games where you, instead of having the second player respond, just have the first player dictate what's the amount to split. Now, do they still give anything to the second player? And how does it, there are actually very interesting set of experiments that have been done on whether or not the outcome is different if the experimenter can't see exactly how people are playing. So part of it might be that there's a measurement issue. So when you're actually playing, the subjects care not only about what's going on in the game, but also how they're perceived by the people doing the experiment. And that can affect their behavior. So is it different if people can act completely anonymously and you can never see who did what and you can't reconstruct? So if you very carefully construct an experiment so you can't tell which subject gave which amount to which other player, then you actually get different outcomes than what happens in these kinds of games. So there's a lot going on here. It's very interesting. Nonetheless, we get, having our toolkit of understanding Nash equilibrium, understanding subgame perfection, understanding backward induction, being able to write these games down. It gives us a toolkit to begin to analyze these things and make some hypotheses. Then we can go and see how people actually behave in these games, see what the predictions are. We can refine the predictions as we change the motivations of the players or add additional things to the game. But there's a lot more to be studied.